Yeah, am I audible? Okay. And are you able to see the screen? Okay. Yes, you are able to now unmute. Okay. Right? Yeah. Okay. Yeah. So let's start with the lecture. Yeah. Okay. Good morning. So have you tried this problem? Anyone got the answer? Or did anyone find out other way to look at it? Okay. So if you have not done it, okay. So let me give you a different approach to look at it. Okay. So I found a very simple approach than this. Okay, which will be very clear that our claim is to show that correlation coefficient belongs to this interval -1, right? Yeah, x comma y, and you know that correlation coefficient is defined as covariance of x comma y divided by sigma x and sigma y, where the sigma x and sigma y are the standard deviation for random variable x and random variable y respectively. Now we know, okay, so you have, so we want to prove this. So how? I have here, I know that variance of x1 plus x2, I know that is going to be a variance of x1 plus variance of x2 plus 2 times covariance of x1 comma x2, right? Similarly, you can also show that similarly variance of x1 minus x2, if you do, their difference is going to be variance of x1 plus variance of x2 minus 2 times covariance of x1 comma x2. So only change, whenever here minus, here is minus, whenever here is plus, here is plus. Okay, what we know further about the variance property is that variance of, which I did it, okay. So what we know is, also we know that variance of that x1 is nothing but a square times variance of x1, right? Okay, so we know all these properties, and so I'm listing out. Moreover, we also know the covariance properties. Okay, that covariance of a x1 comma x2 is equals to a time covariance of x1 comma x2. So I'm just recalling those properties because I'm going to use them straightforward. Now look at this. Okay, variance of x divided by sigma x plus minus y divided by sigma y. Okay, I have these two random variables x and y. So I'm dividing each entry by sigma x. So it will generate another random variable, you can say, or you can say in particular it's x by sigma x, and similarly y by sigma y is defined. Okay, those two are random variables. And just now we have learned that this is going to be variance of x by sigma x plus variance of y divided by sigma y and plus minus 2 times covariance of x by sigma x comma y by sigma. So for plus it will be plus, for minus it will be minus. Now I am going to use this property here and this property here. Okay, so that's going to be further what I will have is this will implies variance of x by sigma x plus minus y divided by sigma y is equals to, so variance of x by sigma x, so 1 by sigma x whole square time variance of x because of this first property, plus 1 upon sigma y square. I'm just writing additional steps over here. Okay, variance of y, those who know what is going to happen, you can skip those steps. And here is going to be plus minus 2, and this 1 by sigma x will common when you apply this one first, and then again it will be applied. So you will have 1 upon sigma x into sigma y. So plus minus 2 times, so 2 is already there, covariance of x comma y divided by sigma x sigma. Now if you carefully look at the first, variance of x is nothing but sigma x square, right? Okay, so 1 by sigma x square times sigma x square is 1 plus minus 2 times this correlation coefficient, right? So this is equals to 2 plus minus 2 times rho xy. Now what? Now, since whether you take the difference or whether you take the plus of two or sum of two random variables, variance is always to be a non-negative, greater than equals to 0. This will be always greater than equals to 0. So what it will give you further is, this will imply 1 plus minus rho x comma y is always greater than equals to 0. Right? 2 is, because 2 is again a positive constant, you can divide both sides. Now, if you go with the plus sign, so this will implies, I'm saying that, so 1 plus rho xy is greater than equals to 0, and 1 minus rho xy is greater than equals to 0. So these together will imply minus 1 less than equals to rho xy less than equals to 1, and this implies the correlation coefficient lies between the values in minus 1. Right? So do anyone have doubt here now? It's a very simple way. Okay, right.
Hello, sir.
Yes.
Sir, we are dividing it by the standard deviation of x, but here x is only a random variable which we are not knowing. Then, like in
Uh, uh,
practically, how are we going to divide it by the standard deviation while we are not knowing the random variables?
so, but it doesn't matter here, right? Because see, it is not required to know x. Okay. See, if x is known, then only sigma x is known, right?
Yes,
Okay. So once I will give you x, you will certainly find out what will means x, and you need to have some prior information like its PDF, okay, or PMF. Then you can certainly find out its standard deviation, or you can say variance. Okay. Similarly for y. Okay, so now what does this mean? See, if you go with this further, I am just going to now, what is this mean? X, so what is x by sigma x is going, yeah. So means you have, if suppose x is taking any value, so let um, uh, you have c belongs to x of omega. Okay, any value in the range space, because I don't know discrete or continuous. Okay, then what are the values this x by sigma x will take? C by sigma x belongs to x of omega, and this is if and only if c by sigma x belongs to x of omega, if and only if c belongs to x of omega. Okay,
okay.
it's a 1-1-1-2 correspondence. So for this this theory means, like, to proving this theoretical result, you don't need any information for random variable x. Is that clear?
Yes, sir.
Okay, right. Okay. Now we have done last time a very important result which named as Markov's inequality. We will see some examples how they are going to be used. Okay. So Markov's inequality stands for a non-negative random variable, means it assumes only non-negative values, or you can say the values on the positive x-axis, you can say. Okay. Then for any value a, x is, for a probability of x greater than equals to a, is going to be bounded by this quantity. And I hope this is very much shows you have mu x, this is mean, and this a is a number, a is strictly greater than 0. Okay, so this giving you certain estimate, okay, and which we have established in the last discussion. Okay, so I'm not going to draw that proof again here. So okay, so it was very simple. So I have proved it for continuous case. Okay, we have started with finding expectation of x is nothing but the x time fx of x dx. Okay, so then since x is a non-negative random variable, means fx of x only assumes the values on the positive x-axis. X cannot assume the negative value, so it's this equal this integral equals to 0 to infinity. That's for sure. Now that is subdivided from 0 to a and a to infinity, because means you want to work with this constant a. Okay, so 0 to a and this is a to infinity. So since this is a positive number, okay, this will turn out to be positive number because of the integral property. Okay, fx of x is non-negative and x is non-negative. So product of non-negative number is non-negative, and if you are integrate over this over the positive side, it is again going to be non-negative. You can use the monotonicity, okay, of the integral operator. So this certainly greater than equals to this, and over this a to infinity interval, x is greater than equals to this. So again, monotonicity of integral will lead to this. So this is a very simple proof. Okay. Now another important result is named as Chebyshev's inequality. Okay, which is going to design the weak law of large number. Okay, means in the long run, if you perform some sequence of random variable, in the long run, what will happen? Okay, and I hope you can understand by long run means like if you are increasing the number of experiment, 1,000, 10,000, and so on. Okay, what will happen there? Okay, so then you will get a theoretical result here. Okay, and that will assure, that will give you a mathematical base to utilize, okay, that fact. Okay, so Chebyshev's inequality stands for any type of random variable which can assume either negative value or positive values or mix of them. Okay, so it can be anywhere on the real line, so range can be anywhere on the real line. Okay, now let's say mu x denotes the mean and variance is sigma x square. Okay, then for any positive k greater than 0, okay, this probability is bounded by variance divided by k square. So can someone try to emphasize that what it signifies, okay, geometrically or physically, you can say? Can someone try to interpret this? Yeah. So what does this denote? Mod of x minus mu x. What you have learned in calculus, what is the
The
absolute value?
So it's a distance between the mean point and the point which we are considering,
Okay,
and we
and
are just
greater than
trying to
equals
limit.
to k.
We are trying to limit
Yeah,
it into some range from like mu x minus k to mu x plus k.
are you sure? It's a greater than equals to, not less than equals to. So this distance is more than k, positive number. Now this, the distance of this is more than this positive number, k is going to be, this probability is bounded by this number. Can you now tell something about it now? Can I read this? The probability that x is going apart from mean, okay, means like probability that this is apart, x, the x value is apart from the mean, means for this uh, if you go with the distance, this if more than, if you k, what it will tends to the right hand side, the probability is going to be 0. So that probability, so the values of, most of the values of x will lie surrounding the mean. Can I interpret this like this? At certain point of time, Okay, after certain amount of time, the probability that it is that the values of x going apart from the mean, that probability is almost negligible. That can I interpret here. Okay, right. I hope you got it. Now, so these two events are equivalent. So, because as you know, it is very difficult with the working with the magnitude. So that's why we are working with the here square. Okay, so mod, whether you work with this set of events or you work with this set of events, okay, both will give you the same result. Okay, right? So let's proceed now. Okay, we are going to work with this. So now see, we are going to instead of we are going to try to evaluate the probability of this set of event. So means we can work with the probability of this set of events. Now note that this x minus mu x whole square will take only positive. See, if you can say if you difference with a constant value of a random variable, it will again give you a random variable. Okay, and if you square it, it will give you non-negative random variable. Okay, because one of them is random, so it will in totality it will become a random variable only. Okay, so this squared one is going to be a non-negative random variable which can assume only non-negative values. Okay, so probability of this, so you can certainly apply the Markov's inequality here. So k is also a positive number. Okay, so probability that x minus mu x whole square greater than equals to k square is less than equals to, if you go and check, x is a non-negative, assume the negative values, non-negative values, and probability that x greater than equals to a is less than equals to mean of this random variable here, which is sitting, divided by a. Okay, so this is what is going to be applied here. So Markov's inequality is applicable, is going to be less than equals to expectation of x minus mu x whole square, this random variable, divided by k square. And now if you look at this closely, what is this? Is nothing but the variance. Okay, so this is sigma x square by k. So this is what we wanted to establish. So it's a simple application of Markov's inequality. Okay, right? So this establishes the Chebyshev's inequality. Okay, now we can state the very important result, which is named as the weak law of large number. Okay, so what this is as follows. So let you have a sequence of identically distributed independent random variables. So let's try to understand this. Okay, identically distributed independent, so they are independent random variables, is be a sequence of independent random variables. And you know what do we mean by a sequence? Okay, x1 x2 x3, so we can, which you can enumerate, you can say. Okay, and identically distributed means what? Both all will share the same PDF or PMF, either they are discrete all and they will share the same PMF, or they are continuous and they will share the same PDF. Okay, so let xi be a sequence of identically distributed independent random variables. In short, you will see its name as IID. Okay, so each having, let's say, mean is mu. So if all share the same random, always share the same PDF or PMF, so they will have the same mean. Okay, right? Then what will happen? So for any epsilon bigger than 0, so Vivek, do you want to say something?
No, sir.
Okay, you raised your hand. So then for any epsilon bigger than 0, what this will give you is probability that mod of x1 my x, this, what is this? Okay, if this is x1 plus x2, this, if you take n numbers, okay, n random variables and divide by n. sum of these n random variables, and that is divided by n. What is this? If you go and work with this data, so this will denote the sample mean. Okay, and this mu is the original mean. Okay, so this is the original mean of each random variable, and this is nothing but the sample mean of the data. Okay, so probability that this mod, the sample mean, is going apart from the mean, which was the mean for x1 or x2 or anyone, because all are IIDs. That probability is more than means that greater than epsilon. The distance is more than epsilon. That probability is tending to 0 as n tends to infinity. So if you fix as large as possible number of samples, it's going to converge to this mean. Right, greater than epsilon. So for any epsilon bigger than 0, so you can take epsilon as small as possible or epsilon as large as possible. So probability that this less than equals to epsilon means 1. Okay, that epsilon however as small as possible. So sample mean will converge to the original mean. Okay, so I hope this interprets this result, and this is again an application of, you can see this mod is there, so it's going to be an application of Chebyshev's inequality. Okay, so we are going to establish the result for whenever the variances are finite. Okay, so see, each x1, x2 and so on, this is a sequence of random variables. So if you take any n, so if you denote, I will denote this y equals to x1 plus x2 plus and so on plus xn by n, or you can say this is yn. I am going to apply Chebyshev's inequality. So what I need mean, right? I need variance of this. Okay, right? I need these two information, variance as well as mean. Okay, so here the mean is what? What is the mean? Expectation of yn. If you use the linear property, so I hope this both sides are pretty much clear here, that one expectation of yn is equals to expectation of x1 plus and so on xn by n. Since expectation is a linear, okay, linear operator, you can say, or it follows it has the linear property. So 1 by n is out, and expectation of x1 plus and so on plus expectation of xn, and since all of them are equal to mu, so n time mu, so n time mu by n, and that's going to be. Okay, now you can also find out the variance here. So variance of yn we can also find out. Okay, so since x1 plus x2 plus xn is again a random variable, so variance of this x1 plus and so on plus xn by n is going to be 1 by n square time variance of x1 plus and so on plus xn. Now since they are IID, independently distributed, so variance of sum of random variable equals to sum of the individual variances as whenever these are independent. So it's going to be 1 by n square summation variance of each xi. I is equals to 1 to n. But all of them will share the same variance because they have the same PDF. If you denote that by sigma, so it is n times sigma, so sigma square, okay, and it will be turn out as sigma square by n. Okay, right? So now, so this is what is here. So sigma x square by, so this is going to be the final one, sigma x square by n. Okay, so variance of yn is this. Okay, now apply the Chebyshev's inequality. So Chebyshev's inequality says that for any k greater than 0, you have the following result. Now take x equals to, means in our word it is a yn, mu is mu, and sigma x square is what? Sigma x square by n, because you have just now find out what is the variance of this. Okay, and that's going to be greater than equals to and k equals to, you can take epsilon. Okay, so once you replace all the things, so you have sigma x square by n time epsilon square, and sigma x square by epsilon square is a fixed quantity when you are increasing n. Okay, so when letting n tends to infinity, this tends to 0. Now see, what we have used indirectly here is, yes, sandwich theorem. Okay, because we know that probability that this is greater than equals to 0. Okay, so left hand side will tends to 0 and right hand side will tends to 0, so this will also tends to 0. Okay, so don't forget that indirectly we are also use this sandwich theorem. Okay, so in the long run the sample mean will converge to the original mean. Okay, right? Okay, so let's we have the one example here. Suppose that it is known that the number of items, suppose that it is known that the number of items produced in a factory during a week is a random variable with mean 50. So I have the only following information. Okay, during a week is a random variable. So if you denote that x, the number of items produced in a factory during a week, then it is going to be a random variable whose mean is expectation value of x is 50. Now, what can be said about the probability that this week's production will exceed 75? So it's very simple. It's a very straightforward application of what you are interested, that probability that if you denote x as the number of items produced in a factory during a week, and you need it is more than 75. So you are estimating the probability that x is greater than 75, and you don't have any information. So it will see this first of all, this random variable is always a non-negative, right? So every week either there will be a production or there will be no production, 0. It will only always take greater than equals to 0, so non-negative random variable. So probability that x greater than 75 is less than equals to expectation of x divided by 75, and which is going to be concluded as 2 by 3. So it's a very straightforward application of Markov's inequality, right? Okay, now what is next here is the following. So if the variance of a week's production is known to equal 25, so you know sigma x square is 25, then what can be said about the probability that this week's production will be between 40 and 60? Means you are interested in this. Okay, so when you have x in the range of something, you are certainly, right, you are mostly you are going to apply Chebyshev's inequality, that you just keep in mind. Okay, so you can rewrite this as follows. I can rewrite this as follows, right? X is lies between 40 to 60. So x minus 50 will lies between minus 10 to plus 10. So it's various ways to do it. Okay, write it down. So I have write it down in one of the way. So it's going to be mod of x minus 50 less than 10. Why I have chosen this 50 here?
Because 50 is mean.
Yes. So because I am interested in applying the Chebyshev's inequality, and Chebyshev's is using here mod x minus mu x, and mu x is a mean. This is why here x minus 50. Okay, so this is important. So mod of x minus 50 is less than 10. Now you can use the probability result, because you know Chebyshev's inequality stands for mod of x minus mu x greater than equals to k. So I just write 1 minus this, right? This is, all these things are true. Okay, now you know the variance is 25, and you know Chebyshev's inequality. Okay, so what it is this is going to be Chebyshev's inequality says that this probability is less than equals to sigma x square divided by this k square. K is 10, so 10 square. So sigma x square is 25 divided by 100, that's going to be 1 by 4. Now if you multiply by minus here, so it will be greater than equals to minus 1 by 4, and this will be the final result. Please do verify whether there is any mistake. So you can see Chebyshev's inequality, we are looking around the mean, about the mean. Okay. And Markov's inequality, look for a random variable which assumes only non-negative values. Okay. Right? It is correct, right? So the production between the number 40 to 60 probability is greater than equals to 3 by 4, so 0.75%. So 75%, right? Okay. Now let's work out with this problem. Suppose that a sequence of IID is performed. Okay, for an event, whether E, so E be a fixed event, and let's say probability of A denotes the probability that E occurs on a given trial. Okay, and let's assume that, see, we need to, okay, we need to specify, then only we can work, right? Because we are now doing example, we are not developing it research. So we are taking, all of them are indicator random variables, and which will notice whether that E occur or does not occur. Okay, so what we say is xi denotes the indicator random variable, and which assumes the value 1 if E occurs on a trial I. So I, so on a trial I, if E occurs, that event E occurs, or 0 if E does not occur on a trial I. So you can look at like you are tossing a coin, whether head you got or not, you will not know. Okay. Now, what this sum will denote then? X1 plus X2 plus Xn. It will denote the number of times that E event occur in the first n trials. I hope you get it. Okay. So X1 plus X2 plus Xn. Okay. This will denote what? This will denote the number of times that E event occur in the first n trials. Okay, so we are interested in looking in the long run what will happen. Okay, so now each, you know, you have already dealt with a indicator random variable, and you are very well known that mean of each random variable is probability of occurrence of E, and we have also found the variance. Okay, what was the variance of an indicator random variable? When the event A occurs or does not occur is probability of A time 1 minus probability of A, if you recall that. Okay, so this is what here. So probability of E time 1 minus probability of E will give you the variance. So for each I. Okay, now let us define this x bar as the sum of n random variables x1 to xn divided by n. Okay, so now you can find out what is the mean of this and what is the variance of this. So you are doing a sampling. Okay, sample mean. Okay, So X bar will denote a sample mean random variable. Okay. So it's very general. Okay, you know very well. So X bar, when you work out the problems in a plus 2 class also, you have denoted sometimes X bar as a summation of Xi's divided by N, right? So expectation of X bar also easy to compute, and variance of X bar is also easy to compute in the similar fashion just now we have done, because these Xi's are independent random variables. Okay. Now what this weak law of large number says, probability that X bar minus mu, X bar is going apart from the mean for any epsilon bigger than 0. Okay, if your distance is more than epsilon, is going to tending to 0 as n tends to infinity. Right? Yes, so what it signifies now? Yes, can anyone interpret here? Now you have everything information. What the variance is showing in the long run. Variance is in the long run is tending to 0. Yeah. So in the long run, variance will be almost negligible, spreading among the values, you can say, of X.
So, sir, we can expect the mean of the random variables to assume just the value of the original mean.
Yeah, original mean only, right? It's going to be, see that probability is 1. Okay, in the long run, the occurrence of the event E, probability is 1. This is what it is showing.
Yes, sir.
Okay. Okay. Now, what the Markov inequality is, because see X bar, each Xi will take in non-negative values, right? 1, 0, 1 or 0. So X bar will also take in non-negative value. So probability that X bar greater than A is less than equals to mu by A. Okay, so we are trying to fit all the inequalities here. So let's try to interpret this now. So if you take A is equals to mu, now what will happen? So probability that X bar is greater than mu is less than equals to 1. And that is that's okay, right? This is a probability property. It is obviously true. And when you take A equals to root mu, the probability of X bar is greater than root mu is less than equals to root mu, right? Whether does this signify this anything? Yeah, what I'm trying to say is, ask you is, so for the case A equals to root mu, probability of X bar greater than square root of mu.
Mu cannot be
is
greater than 1.
Less than equals to what is there is, this is going to be square root of mu. Huh? Why it is saying that this is mu cannot be greater than 1? Mu can be greater than 1.
Because probability cannot be greater than 1. So
No, but here is less than equals to. If you keep an eye here, it's a less than equals to. So if it is more than 1 even, it's still true. Suppose mu is 2. What is square root of 2? 1.414. So probability that X will get the square root of the 2.414, oh sorry, 1.414 is less than equals to 1.414. It is true because probability is always less than 1. So it it's strictly less than even. It's not a problem. Okay, I think this is not giving much information. So let's have the Chebyshev's inequality. Okay, I think Chebyshev's inequality is also giving you the same feeling as we of last night. Okay, because in the long run, again, this K, okay, this is K is there. So in the long run, that going sample mean will going to close to mean the original mean. Okay, so this is what it is again. Interpret the similar thing. Okay, so it will not give you more other information. Okay, right. Okay, now let's move forward to identify now special type of random variables. Okay, so the first random variable which we are going to define as a Bernoulli random variable. Okay, so you can understand Bernoulli random variable that you perform an experiment or a trial, okay, whose outcome you can whose outcome you can look at like either a success or a failure. Okay, means like you are tossing a coin. If you get a head, you will success. If you get a tail, you will be failure. Okay, or you are rolling a dice and you say, if I got an even number, I will win, and if you get an odd number, I will fail. Okay, so you have to divide the possible outcome. You can only classify it as either a success or as a failure. That random variable is known as a Bernoulli random variable. Okay, and its PMF is also straightforward. That probability of success, which we generally denote by that probability of success by P. Okay, and probability of failure is 1 minus P. Okay, so if I read this from the first line, I think you have already have read that. Suppose that a trial is, it's only what I have said, just is in word, that suppose that a trial or an experiment whose outcome can be classified as either a success or as a failure is performed, and let X will take the value 1. So it's also important when the outcome is a success. So when the outcome is a success, X will take the value 1, and 0 when the outcome is a failure. It's a kind of indicator random variable. It's a specialized indicator random variable, you can say. Because it's a specialized, why? Because it can only take value 1 or 0. Okay. But indicator random variables put to it negative values, positive values, all type of values. Okay. So here in this case, when the outcome is a success, X will take the value 1 with probability P, and it will, when the outcome is a failure, it will take the value 0 with probability 1 minus P. Okay, right? So it's denote the PMF of Bernoulli random variable. Okay, because X assumes either of the value 1 or 0 with probability P and 1 minus P respectively. Okay, so this is the definition here, very clear cut definition. Okay, that a random variable X is said to be a Bernoulli random variable if it assumes the value 0 or 1 and its PMF is given by the following. Okay, so probability of X equals to 0 is 1 minus P and X equals to 1 is P. So P denotes the probability of success. Okay, right? Now, if you repeat this Bernoulli trials n time, okay, if you repeat this Bernoulli trial, so when you run a trial, okay, when you perform a trial, if you only notice either a success or a failure for the particular case, means you success or fail. And if you repeat this n time, then what you will see? How many times you will get a success. Okay, right? So, or in other words, sum of n Bernoulli random variables. Okay, which will take the values from 0 to n. Right? So that will, so Bernoulli trial will leads towards the binomial random variable. Okay, so here it is. I'm just now what I've said just now. Okay, let me conclude here. Suppose that n independent Bernoulli trials are to be formed. Say, let's say I equals to 1 to n. Okay, and so Bernoulli trial means each trial results in a success or a failure. So let's say, assume that each trial results in a success with probability p and in a failure with probability 1 minus 1. Okay, so let x will denote the sum of these n Bernoulli trials. So what it will be equals to, if you read it, this, what is this physically is number of successes that occurs in the n trials. So it may be 1 success, 2 success, or no success. Okay, in n number of trials. So if you toss n point n times, it may possible that all the n time you will not get head. It is possible. Okay, or all of them may be head, right? Or number of time is head and n minus I number of time is tail. So this x will take the values from 0 to n. Okay, now it is important now. So this is going to, now it is important to identify the PMF. Okay, so this again, this will assume the discrete value, so it's going to be a discrete random variable. So Bernoulli is also a discrete random variable, and this will x will also identifies the discrete random variable, and which will be named as binomial. Why binomial? You will know. Okay, or you may already know. Okay, why it is named as binomial. Okay, so PMF I have, so you have, this is x belongs to 0 to n, and we will, so here is the notation. Okay, that it will follow the binomial distribution. Okay, so with 2 parameters. Okay, either we'll say binomial distribution or random variable, both are the same thing. Okay, so binomial with parameter n and p. So what this n will signifies? N will signifies number of times independent trials performed, and p will denote the probability of success in each trial. Okay, now it is important to identify its PMF. Okay, so if you let me now you are interested in finding the, so x can take any values from 0 to n, 0, 1 to n, and we are interested to identify what is the probability of x equals to I. Means what? What is the x equals to I means? Probability of number of success is I, and number of failures is, what is, this is the meaning, right? Failure is n minus I, right? Now see, you are repeatedly, you are doing n number of trials, means they are independent. Okay, so number of success is I out of n, and number of failure is n minus I. So p into and so on, I times, and 1 minus p is the probability of failure, right? And so on, 1 minus p, that will be n minus I times. Now these things can be, okay, can have any order, okay, means first is failure, second is success, third is success, fourth is failure, and so on. So how many such possible cases will be NCI? So out of n, I is success, okay, so that will give you the NCI. So n choose I. So now this is equals to NCI times p to the power I times 1 minus p times 1 minus p to the power n minus I, with I equals to 0, 1, 2, and so on. So this will give you the PML. Now this you saw, if you recall, this is nothing but the binomial coefficient. Okay. Now if you look at the following, 1 plus p plus 1 minus p to the power n. You know a plus b to the power n. Okay, you know how it is. Okay, this is going to be summation, right? NCI p to the power I 1 minus p to the power n minus I equals to 0 to n. And left hand side is nothing but 1. So the total probability, so probability of x equals to 0 plus x equals to 1 plus and so on, probability of x equals to n is equals to 1. It will give you that also. Okay, and this NCI is nothing but the binomial coefficient of this expansion. This is why it is known as binomial random variable. Okay, right. So this is just now explained. Okay, okay. So now about the binomial random variable, you need to identify the number of independent trials and probability of success in each trial. Okay, if you know, you can get this into information. Okay, and expectation of x is n time p and variance of x is this. We are going to work out with this. Okay, so but if this is true, what it tells you is variance is going to be smaller than mean in the case of binomial random variable. It's very straightforward, right? N time p time 1 minus p is less than n time p because 1 minus p is less than. So it's very straightforward. So variance x, so see the variance is going to be smaller than mean. Okay. Now, if you now look at this, so now let's try to prove this expectation of x is n time p. Okay, so we want to establish this result. So there are two ways. Okay, I will try to explain the both ways. Okay, means very simple way is also there, so that we also try to see. But if you try to go with the direct definition, expectation of x is equals to, what is that? It's a discrete random variable. So summation x time px of x, and x will range over the all values of x, right? So if you go with that, so expectation of x is equals to the following, right? Okay, so expectation of x is equals to this, right? Now you substitute the value of that the probability that x equals to I is equals to this. Now expand this NCI. You know what is the NCI? Is n factorial divided by n minus I factorial time I factorial, and if you cancel with this I, you have I minus 1 factorial here. And now you are arranging. Okay, now you are rearranging the terms here. Something you need to take out, what is that is n time p. Why it is so that this is going to be an expansion of some a plus b to the power n minus 1 or n minus I, whatever. Okay, so n factorial can be written as n time n minus 1 factorial. Okay, so n will come out from here. Now p to the power I, p will also will come out, that is p, and it here what it will remain is p time I, p to the power I minus 1. Now see, the first sum here I equals to 0 to n. The second sum is I equals to 1 to n. Why? Can anyone tell? If you noticed, I have I equals to 0 to n, and second sum I have I equals to 1. Why? Yes?
N equal to 0 will be
Because
0.
yes,
Yeah,
sir.
I equals to 0 will not contribute anything because I is sitting in the product here, so I equals to 0 will not lead anything. So this is why our life is simple here, because if I equals to 0, p to the power minus 1 may create some difference, or may create some problem later on. Okay, so this is why I just want to verify it again back. Okay, and n time p is out, and now if you look at this coefficient carefully, is nothing but it's nothing but you have, if you look at this, it's nothing but n minus 1 c I minus 1. Right? So this is nothing but n minus 1 c I minus 1. And now this together, because I is here 1 from 1 to n. Okay, so n minus 1 c is 0, the first entry, and last entry is when you have I equals to n is n minus 1 c n minus 1. So I can write this as this total block, this one, as p plus 1 minus p to the power n minus 1. And since this is p plus 1 minus p, is again p will get cancelled, and 1 to the power n minus 1 is 1, and you will remain with n time p. Right? So it will be, so this is what we have faced the problem with respect to expectation of x. When you go with the variance of x, you will again you have to deal with such type of problem. Okay, again you have to arrange the coefficients and so on. So what is the alternate here is to look at the basic of binomial random variable. So binomial random variable with the n number of independent trial is nothing but you can treat them as a sum of n Bernoulli random variables, and you know what are the variance and what is the mean of each Bernoulli random variable. That was simple, right? So I'm going to use that. Okay, right? So this is okay, fine. Now if you see, so this is what it is I'm stating here. So x follows binomial, means x equals to x1 plus x2 plus and so on plus xn, sum of n independent Bernoulli trials with probability of success p in each trial. Now see, it is how it is simple now. Expectation of x is nothing but summation of I equals to 1 to n expectation of xi. Now each expectation of xi is nothing but p. How many times is n time? Very straightforward. Similarly, variance of x, since they are independent random variables, so variance of summation of xi is nothing but summation of individual variances, and variance of Bernoulli random variable is p time 1 minus p for each I, n time this, and it's simple. So basic sometimes helps you a lot in this case. Right? So x has the means if x follows the binomial random variable with n number of independent trial and p as a probability of success, then its mean is going to be n time p, and variance of x is n time p time 1 minus. Okay, right? So the thing is clear. Okay, now Let's do this problem. Okay, read it. Okay, so it is known that discs produced by a certain company will be defective with probability 0.01 independently of each other. Okay, so discs produced by a certain company will be defective. So will be defective with probability 0.0. Either the disc will be defective or it will work. Okay, so defective probability you can treat as like either a failure or success with probability 0.01 and failure with probability 0.99 or either otherwise. Okay, other way around. Okay, and each disk you should treat them as independently. So if you name them x1, x2 and so on, so all will denote the Bernoulli trials. Okay, right. Now the company sells the disk in packages of 10. So if you go and buy, okay, then you have to buy a package of 10. Okay, means if x1 plus x2 plus and so on plus x10, and you know some of these 10 Bernoulli trials will converge to the binomial. Okay, with 10 as the n value and p is the probability of success. If you denote 0.01, it will be defective. Okay, and 0.99 is 1 minus p. Okay, so you have all that information. Okay, and what the company is doing is the company offers a money back guarantee that at most one of the 10 disks is defective. Okay, so it is giving money back guarantee that at most one of the 10 disks, means it says that if more than one disk is defective, means x greater than equals to 2, okay, then it will give you the money back guarantee. Okay, what proportion of package is returned? Okay, right? So you have all the information. I have tried to model it in a certain scenario and I hope you get it. Okay, so what I just now said is, here it is. So let x denotes the number of defective disks in a package. Okay, so x will take any values, number of defective disks, it be 0 or all of them are could be defective. So 0, 1, 2 and so on 10, all values it will take. Okay, so since each disk will be defective with probability 0.01 and non-defective with probability 0.99, therefore it is a Bernoulli trial. So you can denote them as that. Okay. Now, also these Bernoulli trials are independent of each other because your disks are defective or not defective independently. Okay. So therefore x will follow the binomial distribution with this. And it offers a money back guarantee that at most one disk of 10 is defective. So you need probability of x greater than 1, means the package returned. Okay, the package returning probability you need to find out. So it will return only when you have more than one disk in the package is defective. So probability of x greater than 1 is going to be is equals to 1 minus probability of x less than equals to 1, and it's going to be 1 minus probability of x equals to 0 minus probability of x equals to 1. And if you fix all the values, you know x follows the binomial distribution, and you know the PMF, if you fix them, it's going to be 0.00. So the package will return with the probability 0.005. Okay, right? Do anyone have doubt? Okay, so this is what it is written is the law of null number. It follows that in the long run 0.5% of the packages will have to be replaced. Okay, so this is very easy to follow. So each package, see, each package you can look at like a, again, if you so each package either it will be returning or it will not be returning. You can treat that, so it will be returning with probability 0.005 and it will not be returning with the probability point you have 995. Okay, so either probability of success and probability of failures, you can again treat them as a Bernoulli trials. Okay, and this will take value 1, how many packages will return or how many packages will not return. And you know the law of large number says that in the long run, right? So what is the mean is 0.005, right? Mean of that Bernoulli trial is 0.005, right? So in the long run, so 0.005, if you make it as a percentage, it's going to be 0.5% of the packages will have to be replaced. So it's going to be, right? That's the law of large number says. Okay. Now I left this question to you that if someone buys 3 packages, what is the probability that exactly one of them is returned? Okay. I have given you every clue here. Okay. Package will return with probability 0.005. Will not be returning with probability 0.995. So returning is a probability of success, you can say, and not returning can be treated as a probability of failure. Okay, what is the probability that exactly one of the package will be returned or really replaced, whatever you say? Okay, hint is this will again will follow a binomial random variable with n equals to 3 and p equals to 0.005, and you need probability of x equals to 1. Okay, it's very simple. Okay, and I think his answer is here. Yeah. Okay, right. Fine. I think we can close here. Okay. Yeah. So we can close here. Thank you. If you have any question, you can ask. Okay. Thank you.
Hello, sir. I am having a doubt.
Yeah.
Sir,
Yeah.
sir, can we say that in the indicator random variable is also a Bernoulli random variable, because there the indicator random variable took the value 0 or 1 depending on whether the event not occurred or occurred respectively.
Pardon? I have lost some where you tell again. Say it.
Sir, can you please, sir, can we say that an indicator random variable is a Bernoulli random variable? Because,
No.
sir, an
I
indicator.
said no. I said Bernoulli random variable is a specialized indicator random variable. Okay, so it is a fixed. So it's a fixed type of means which take value 1 if probability success, I mean if event occurred, and it will take value 0 if event does not occur. But on the other hand, event that indicator random variable can take negative value as well and positive values as well. Anyone. Okay, it may take -2 when probability of that event B occurs, and 0 if event does not occur. So indicator random variable can take any value, positive value or negative values. So Bernoulli trial is a specialized indicator random.
Okay, sir.
Okay.
Yes, sir.
Yeah. Okay. Thank you.